Hey Panthers! This is lesson 2 of the topic in your remote learning book, Expressions and Equations. If you haven't completed lesson 1, the link for the video is below. And if you're ready to move on, make sure you've got your remote learning book and something to write with as you follow through this lesson.
So let's just dive right into lesson 2 on equivalent equations. If you do not have your remote learning book directly in front of you, pause the video, go grab it, and come right back for the guided lesson. Reminder that pause and play feature is extremely beneficial as you are learning, understanding, and writing down information into your remote learning book. So use that pause and play feature as much as you can. You guys have basically a remote to your teacher. So remembering we're talking about equivalent expressions this lesson, and that word equivalent is something that we've talked about multiple times. I just want to make sure you have a quick refresher. Equivalent means equal or the same as. So whenever they're asking us, like in this first case, to write an expression that is equivalent to this one, we're going to try to find an expression that's the same as or equal to this one. Just a quick little reminder on the definition of equivalent. So let's look at this math page. This is using what we know. This is our review page, but it kind of helps us in the sense that we use what we already know how to do. And on this page, it kind of tries to take that first building step into your new topic. So in this case, we know this expression 3 plus 14 plus 27. We could solve this equation or this expression, but we're not just going to simply solve it. We're going to kind of go into a little bit of depth about changing its value and finding an equivalent or equal expression. So let's start with A. Which two terms in this expression, reminder that we've got these parentheses and you can't just get rid of parentheses. It says, which two terms can get you a multiple of 10? We have 3 terms here because remember a term, that definition, one of those definitions is a known number. So in this case, I have 1, 2, 3 known numbers, so I have 3 terms. Now, which of those could be added together to get a multiple of 10? 3 and 27. I could add those two together and get 30, which is a multiple of the number 10. 10 times 3 is 30, meaning it's a multiple. So it says to rewrite the expression so that these two terms are next to each other. So all I can really do is change the order in that parenthesis. I'm going to put my 14 first, and then I'm going to add the 3, and then I'm going to put the 27 together. Just because I know that when I put these two together, I'm going to get a multiple. So I rewrote it so that the easy numbers, the numbers I know that I can add together to get an easy number, are right by each other. But did this change the value of the expression? If I were to solve this expression here, and if I were to solve the expression up here, would it be the same? 100%. So I did not change the value. Because when you're adding numbers, the sum, the order of the numbers does not matter when you're adding. So the order of the numbers, when you're doing things like dividing and subtracting, the order of the numbers is crucial. It's 100% important, but when you're adding and multiplying, the order doesn't quite matter because it's commutative and means that no matter the order, you'll get the same answer. So D says rewrite the expression with parentheses to show that the two terms with the sum that is a multiple of 10 should be added first. Okay, so now I'm moving things in and out of my parentheses. I'm going to change it. I'm going to leave my 14 out of the parentheses and do 14 plus, and then I'm going to show by putting 3 plus 27 in parentheses, I am showing you the first step. I'm basically saying, hey, look over here and do 3 plus 27 first. It's in the parentheses, so if you're doing order of operations, you would do that first. And then you're going to get an easy number versus if you were up here, 14 plus 3, you're going to get not an easy number. So rewriting the expression does not change the value. When I rewrote it from the first to here, where I just changed the order of the number, I 100% didn't change it. But even when I switched where that parenthesis was, I still am not changing the value of this expression, because you can add, again, the order of the numbers doesn't matter. So you can add any two numbers together first. So when adding, oops, I got my capital locks all sorts of messed up. When adding, you can add any two terms together first, and the sum stays the same. That is the key right there. The sum stays the same, which is the answer. The answer will always be the same. If you were to change the order in a division problem or a subtraction problem, the answer will not stay the same. And that is what we're getting to. What is the common factor of the numbers in the parentheses? So right now I've got two numbers in parentheses. We're looking at D, and those numbers are 3 and 27. Remembering, factors are going to be the numbers that you can multiply to get to these numbers. This case is pretty easy because my first number is a small number and it only has two factors. And those two factors are 1 and 3. Because I can multiply 1 times 3 and I can get 3, and there's no other two numbers I can multiply to get to 3. 27 is a little bit more difficult because it's got multiple factors. I can multiply 1 times 27. I can multiply 9 times 3 to get to 27. So they have factors of 1, 3, 9, and 27. So when I'm trying to think of what my common factor is between those two, I'm trying to think of what is the number that is in both of those. And in this case, the common factor between 3 and 27 is 3. And having a smaller number makes it a little bit easier to figure out what the common factor is, simply because the smaller numbers, they don't have a lot of factors. So it's pretty easy to figure out, okay, in this case, I got 1 and I got 3 as my two factors. Okay, well, I know 1 goes into 27, but does 3? Oh, shoot, it does. So that's going to be my common factor, is 3. Rewrite the expression so that the number plus the product of, rewrite the expression so that it is a number plus the product of a number and a sum. Uh-oh. So now they're telling us that they want us to use this common factor 3 to pull out these numbers and figure out a different way to rewrite this expression. So again, I'm going to leave that 14 alone. I'm going to go ahead and just put 14 plus, because it is saying 100% the same. Now where they're asking me to change it is in my second, in my parentheses. And they want me to do something that we kind of sort of worked on towards the end of our time in school, but that is pulling out that common factor and putting it on the outside of the parentheses, and then using the distributive factor to distribute it back in and multiply it. So I'm going to show you this example first. We're going to get into it a little bit better as we dive deeper into the lesson. So in this case, my common factor, which I figured out from F, was 3. So I'm going to pull that 3 out of my parentheses. Now, whenever I see something on the outside of my parentheses, I know that that number is going to multiply the numbers that are inside this parenthesis. So now I have to go back to my problem up here, and I have to say, what do I have to multiply? I pulled that 3 out. So what do I multiply 3 by to get to 3? So if you look, I'm going back and forth between G and D. So I multiplied 3 times 1 to get to 3. So inside my parenthesis, I'm going to write that number 1, because I know that I'm going to end up having to multiply 1 times this 3, and I want to get the same answer that I've got up here. So let's continue with the 27. What can I multiply times 3 to get to 27, and that answer is 9. So if you look down at my answer for G, I've got 14 plus 3, parenthesis 1 plus 9. And I want to show you very quickly before I move on to H, and this is kind of like a little bit of an in-depth of this other part of this assignment, but I need you to understand it. Here, when we're looking at 14 plus 3 times 1 plus 9, we need to think of this. When we're doing the distributive property, the 14 is going to stay the same. What we did here was we pulled out that 3 so that we could multiply it. If I were to rewrite this problem after distributing it, I should be able to go 14 plus, and then 3 times 1 is what? So 3 times 1 is 3. And then I should be able to do, here's my operation symbol, my plus, or my equal, or my division. Plus, and then what's 3 times 9? And that answer is 27. So I can see that if I write this problem as this way, and then I do the distributive property, that I can get right back to that same answer that I got in D. So let's use that information to write down the answer for H. Does rewriting the expression change the value? Nope, it doesn't. Because we get 14 when we do the distributive property, we get the expression 14 plus 3 plus 27, which is our answer for D. And it really shows that even as long as we make sure that the math that we're doing is correct, when we are pulling out numbers to multiply, as long as we can make sure that we're moving numbers around that are being added, then they're not changing the actual sum or the value or the answer of your expression. So explain why you might want to write an equivalent expression. So sometimes when you can write it as equivalent, it makes it easier to solve. So it can make the problem easier to solve or simplify anything. So like looking right here, these two, this equation, 14 plus 3 times 1 plus 9 in parentheses, is equal to 14 plus 3 plus 27, which is equal to 14 plus 3 plus 27, which is also equal to our original expression of 3 plus 14 plus 27. So if you really look at, all of this, we have this one. And this isn't quite an equivalent expression, excuse me, because it is using all the same numbers, but we were just showing you that you can move things around and it's still the same. And down here, you can move things around, it's still the same. And here's where we really changed it. We went from just doing simple, addition, and now we've got multiplication involved. I can see that this is a completely different expression, but when it all comes down to it, will I get the same answer in the end? Absolutely. So then here is our forever important note page, which I always highlight in yellow. And I'm just going to quickly go over this. A great resource whenever you're doing independent work. If you have any questions, always come back to the highlighted page. It's always a great notes. It says, in the problem on the previous page, you apply the properties of operations. We've talked about these properties. I've been using them as I was explaining that first page, the cumulative property, the associative property, and the distributive property. We have gone over these in class, anchor charts. 5th grade was a really big year in learning these things. I will throw the Brain Pop and Khan Academy at the end of this lesson just to make sure that if you are struggling with these smaller parts of the bigger lesson that you can, get yourself some background knowledge and some foundational skills and work so that way you can be successful. So the commutative property basically tells us that when we have order, the order of the terms does not change our final answer. In addition, so we also, since we've already dove a little bit deeper into the commutative property, we know that this also is the case for multiplication as well. So that's something to keep in mind as we continue. But then we also have the associative property, which means that regrouping them or changing where your parentheses are doesn't change the value or the answer of the expression. And then the last one that they wanted to talk about is the distributive property, which means that taking the common factor out of the parenthesis, like in this case we had 3 and 27, the common factor was 3, we took it out. Then we can use that common factor and we can have smaller numbers inside and we can multiply. But the distributive property, in addition, does not change the value or the answer again. So when you have variables in your terms, the same thing is 100% true. As you can see, all they did was add in a variable or a letter x, and they took this first one, they show the commutative property where they switch the order and it still gives you the same answer. And the second one, they showed the associative property where they change the parentheses and it doesn't change the answer. And in this case, we can see that they took out the coefficient next to the x, which is something that we might think of later when we're doing the a little bit harder examples, that we can just take that coefficient right out of our parentheses and use that to multiply in the distributive property without changing the answer. So let's reflect. Henry says that you can apply the commutative associative properties to 5x plus 10 and get 10x plus 5. Is he right? No way. Henry, you got it all backwards. So 5x and 10 are the terms in the original problem, right? So 5x and 10 are the original terms. In this case, Henry changed or altered the terms to come up with his equivalent expression. If I could absolutely type. You cannot change the terms. Can't just say, oh, you know what, I want to change that. I want to take that x from the 5 and I'm going to put it onto the 10 because it changes the value. So when you change the terms, it changes the value. And the biggest thing when we're talking about equivalent expressions is that the value is the same. So the commutative and the associative properties, they say that we can reorder and regroup the terms of an expression, but if you change the actual term itself, then it's going to change the value. So by changing the 5x to 10x, that is what made Henry incorrect, and that's why Henry's value of its expression would change in the long run. So reminder, slide 3 is your note slide talking about the commutative properties. The first slide, the review slide, really breaks it down, so this might be another spot where you could find some good support. So let's get right into our modeling and guided instruction. So Jamie's got 4 bags of apples and Ashley has 3 bags of apples. Each bag has the same number of apples in it. So after this problem, what we're gonna do is write the expression and then simplifying it to create an equivalent expression. So the first thing that iReady always has you do is draw a picture, and it's super helpful. And I know I say this all the time, but when you can connect words to a diagram and then to the overall math and equations, it really kind of makes more sense in your head. So in this case, they drew Jamie's 4 bags and Ashley's 3 bags, where each bag has X amount of apples. Because reminder, we have zero idea the number of apples in each bag. So that's all she drew for her picture. And then she drew it with the tiles, which is essentially the same. She's showing the same thing. We can see 1, 2, 3, 4 bags with X amount of apples. Ashley's got 3 bags with X amount of apples. So we can see how we can go from thinking about what the words are saying and thinking in terms of apples, and then we can see the model it. They don't really focus on the apples aspect. They're really trying to focus on more of the math aspect. How, like, the number, the X, it kind of gets rid of the pictures and really takes it into like a math diagram. So let's go to the Connect It. Reminder, I can't show you 2 pages at a time, so it's really important that you are looking at the previous page as we go over the Connect It on page number, whatever number that this is now, 100 and, let's see where we're at, 113. So you should be looking at the pictures on page 112 as we answer the questions on page 113. In both the Picture It and the Model It on the previous page, what does the X represent? So the X represents the unknown amount of apples, because we have zero idea of how many apples in each bag. So and then it says write an expression for Jamie's total number of apples. So if I'm looking back on page 112, I'm simply looking at Jamie. I know that Jamie has 4 bags of apples that have X apples in each bag. So Jamie's expression for her total amount of apples is going to be 4 times X, because there are X amount of apples in each bag and she has 4 bags. And then for Ashley's total number of apples, the same exact concept, except for Ashley only has 3 bags of apples, so it'll be 3x, so 3 times x. Write an expression for the combined total of Jamie and Ashley's apples. So if we wanted to know how many apples did they have all together, we would have to add 4x and 3x together. 4x plus 3x would give us the total amount of apples that both Jamie and Ashley have all together. And then, so now that we've come up with that expression, it says when 2 or more terms in a variable expression have the same variable factors, they are called like terms. We've talked about combining like terms often. You can use the distributive property to simplify an expression with like terms. So what is the common factor for each term in problem 3? So the common thing, I'm trying to think, 4 and 3, that doesn't seem very common, but they both have an x. So our common factor for both of these is x. I know that I can't multiply something to get to 3 and to get to 4, so my common factor is going to just strictly be x. It says distribute the common factor and simplify the expression. So basically, they want us to show we have 4x plus 3x. And if we were to work like we did in the review page and pulling out that common factor, in this case, if I look at number 4, that common factor is x. So if I were to pull that x on the outside of some parentheses, and I know that when I pull that x out, I've got to multiply it times whatever numbers are inside the parentheses. So if I were to take the x away, I would multiply 4 plus 3. And so this way, if I were to distribute this, I would have x times 4, which is 4x, and then x times 3, which is 3x. So by actually doing the distributive property, either in my head or on a piece of paper, after I do it, I can check my answer, make sure that I'm on the right track. So from here, they really just wanted me to show you that this is one way. You can pull out that x and you can show it as a distributed. This is how you would show it to be in the distributive distributive factor. Yeah, like the distributive property. That's what I'm looking for. But I also need you to be able to show that if I were to write this as x and then I added together, what's 3 plus 4? So x times 7, and then I can distribute that x in there and I could get that my final answer would be 7x. So I guess that the overall question is this right here, 7x, equivalent to 3x plus 4x? So in the simplified expression, the answer is yes. Because if I think about how many total bags did Jamie and Ashley have all together, then answer 7. They have 7 bags of apples. So if I know that there are X apples in each bag, then it doesn't matter how many bags each girl has. I know that I have 7 total bags together, and I can just multiply that by the amount of apples in each bag. Explain how to simplify an expression with like terms, such as 6g plus 5g. So it says, so what we would have to do is factor out our common factor. So factor, I'm trying to write these as step-by-step instructions. Therefore, if you get caught in your independent work, you can come back here. So factor out the common factor, which is our first step. In this case, my common factor is g. I have a g in both terms, and I know that I can't multiply anything to come up with 6 and 5 and have a common factor other than 1. So I'm going to factor out my common factor, which is g, and I'm going to rewrite this problem as I'm taking that g out, and I'm going to put my 6 plus 5. And really quick, before I even get into the finishing of simplifying, I'm going to check my answer so that if I continue working and I have a wrong answer, my answer is only going to get more wrong. If I can stop on step 2, or step 1 in this case, and realize that I made a mistake, it makes the rest of my life a lot easier. So checking your answer here is kind of important. Making sure whatever you factored out for your common factor, you're multiplying that in. And when you multiply it times each of these interior numbers in the parenthesis, you should get the same exact expression. So in this case, I would do g times 6, and I would get 6g, and then plus g times 5, which is 5g. So I know that this right here, if I were to distribute it, I would absolutely get that same answer, and that is a great self-check. From here, I factored out my common factor, and then now I'm going to simplify 6 plus 5. Which is what's inside my parenthesis. 6 plus 5 is 11. So now I have g times 11. And then from there, I distribute. I'm trying to make this so I distribute from there. And then if I distribute g times 11, I get 11g. And that right there is your final answer of simplifying 6g plus 5g. And I know that that seems like a ton of work. Another way that I like to just do it is, hey, if these both have the same variable, I just kind of do what's 6 plus 5, and I know that that answer is 11 in my head, and then I just leave the g. So, I mean, again, I've been doing math for a lot longer, so you might want to go through these steps and just making sure that you're getting the correct answer. We're going to move into the try it. I will be doing these on the dry erase board, numbers 8 and 9. So this is a school cafeteria has 30 boxes of Wheaties Squares cereal and 20 boxes of Mighty O's cereal. Each box has the same number of ounces of cereal. Write an expression to represent the total ounces of cereal. Then simplify it to create an equivalent expression. So, looking on the board, I am going to start by writing my original expression. And I can see that they have 30 boxes of Wheat Square cereal and 20 boxes of Mighty O's, and they both have the same number of ounces of cereal. So in my head, I'm trying to think of what is the number that I don't know of? Like, what is my variable? And in this case, the number I don't know is the ounces of cereal. So I know that my variable X is going to be the ounces of cereal. And then from there, I can say that they've got 30 boxes of one type of cereal, and they've got 20 boxes of the other type of cereal. They want me to write an expression to represent the total ounces. So I'm going to add, when I see total ounces, I know that rings a bell and the keyword there, and I'm thinking of addition. So I'm going to put my addition sign, and I'm thinking about my two terms that are going to go on both sides. The first term is going to be the amount of ounces of Wheaties Squares cereal. I have 30 boxes, so I'm going to write my 30, and I have X amount of ounces because I have zero idea how many ounces per box. So I'm going to write this as 30X. And then to turn around and do my Mighty-O's, I've got 20 boxes of Mighty-O's, and again, I don't know how many ounces are per box. So I'm going to write it as 20X. So I've got an expression of 30X plus 20X. And now step 2 is asking me to create an equivalent expression. So if I were going to do our step-by-step instructions, I would factor out my common factor first. In this case, it's X. So I've got an X over here, and I've got an X in 30. So I'm going to pull my X out, and then I'm going to keep those two original coefficients. So I'm going to X, and then I'm going to put the 30 plus 20 inside the parentheses. And if I wanted to double check myself here, I would go back and do the distributive property. X times 30 is 30X, and X times 20 is 20X, and I can double check that with my original equation, and they match, so I'm going to move on. From here, I am simplifying. So I've got 30 and 20 inside my parentheses. I'm going to add those two together. 30 plus 20 is 50, so now I've got X times 50. If I were to show the distributive property there of doing X times 50, I get a final answer of 50X. And reminder again, if you're looking for the shortcut, I think that looking at the 30 and X plus the 20X, taking your coefficients, which are the numbers in front of your variable, adding them together, and then just throwing a variable at the end is also a shorter, faster way to do this. But as you're trying to learn and understand how they're equivalent, I think it's important that we make sure we go through those step-by-step instructions. So let's look at number 9. And the inspector at a bottling plant checks 25 bottles. 2 bottles do not pass inspection. All the bottles hold the same number of milliliters of sports drink. Write an expression for the milliliters of sports drink that pass inspection. Okay. And then we have to simplify it. So let's think about, they check 25 bottles and 2 do not pass. They all hold the same number of milliliters. So in my head, I don't know how many milliliters are in each bottle. So I'm thinking that my variable is going to be the number of milliliters per sports drink. And then when I'm going to write this expression, my first step is always going to be to think about what operation am I using. So they say all the bottles hold the same number of sports drink. Write an expression for the milliliters of sports drink that pass inspection. So I have to think that there were 25 bottles and 2 didn't, and I need to think about their ounces and how many altogether do I have. I'm going to subtract here. So I'm going to write down my subtraction sign, and then I need to figure out term 1 and I need to figure out term 2. And how I'm going to figure that out is I know that they started off with 25 bottles. And I know that of those 25 bottles, they have X amount of milliliters per bottle. So I have this term of 25X. And if I multiply the amount of bottles, 25, times the amount of milliliters that they have, I will get the total amount of milliliters in 25 bottles of sports drink. 2 bottles do not pass inspection. So I'm going to write that down because I know I'm trying to figure out how many did pass inspection altogether. So 25x minus 2x. And the reason why we're adding that x there is because those are ounces of soda, or those are milliliters of soda that did not pass inspection. So we need to multiply that times our variable x, which is going to be the number of milliliters. So now I've got this expression 25x minus 2x. And if I wanted to simplify it, I'm going to look at both of those things. I'm going to pull out my common factor, which is x. And I'm going to put a parenthesis. I'm going to write down my two coefficients, 25. And then this one is a little bit different because if you notice in the middle, I have a subtraction sign. So this isn't going to be 25 plus, it's going to be 25 minus 2. So my distributed, if I were to put this into the distributive property, I get x parenthesis 25 minus 2. And really quickly, if I wanted to check it, I would do x times 25, 25x, and x times minus 2, minus 2x. So I get 25x minus 2x, which is the same as my original problem, which means I can move on. So from here, I am going to do 25 minus 2, which is 23. And then from there, I'll take my x and distribute it. X times 23 is 23x. So therefore, my final answer would be 23x. And again, if you want to look at your coefficients in your original problem, you got 25 minus 2, and then you can just take your variable from the end of it and then just add it. But for the sake of actually understanding what's happening here, I think it's important that you're going through this step by step. So let's go on to the properties of equivalent expressions. So this is Javier creates a rectangular painting. The painting is 3 feet long and more than 2 feet wide. The expression 3 times 2 plus x represents the area of the painting. Write an expression equivalent to 3 times 2 plus x. So the first step that iReady always takes is the modeling it and the picturing it. So the first thing, it says the multiplication expression 3 times 2 plus x means 3 groups. If you look, you have 1, 2, 3 groups of 2 plus x. So I want you to think of everything that's in the parenthesis of being a group. So 2 plus x is our group. We got 1, 2 are the yellow squares, and the x is going to be an unknown number because it's a variable, and that's going to be represented by this green rectangle. The 3 on the outside is showing you the amount of groups of 2 plus x. So there is 1, 2, 3 groups of 2 plus x. So when I look at those 3 groups, I see it here. And then if you reordered it and you added your like terms, so if I just took all my yellow squares, which I know that I have 2 in each group, I would have 2 plus 2 plus 2. And then if I had all my x's, I would have x plus x plus x. And now I can think about this problem, this original problem, as 3 times 2 plus x, as 2 plus 2 plus 2 plus x plus x plus x. They are absolutely the same thing. My value never changed. I just reordered it and regrouped it. But I can do that as long as I'm doing addition. So here's your picturing it. And if you wanted to draw and label a picture, we know that the width of the picture is 3 feet. And then they said the length is. Then the width is going to be a little bit more than 2 feet wide. So we're always thinking about the area. So here's our 3 and our 2, and here's the x with a little bit more than 2 feet wide. So the area of this entire painting is going to be because remember, whenever we're doing length times width, we're going to do 3 times 2 plus x. And using these are going to be very beneficial as we move on to our next guided instruction. So now we're going to get into determining whether or not expressions are equivalent and the quickest way to determine that. We're going to be looking at the expressions 5x or 5h plus 2h squared, and we're going to ask ourselves, is that equivalent or equal to 7h? In the picture they show us what we don't know the number for h. It's an unknown number. That's why it's a variable. So they gave us they made this line segment to be the length that is h. Even though we have no idea what the actual number is, this line segment I can look at and say that is h long. And the next one underneath it, I can say they took h and they multiplied it times 5, and this line segment is 5h long. And then they took that same h line segment and they multiplied that 7 times, and that would be what the 7h line looks like. So while we don't really have an exact number of h, a lot of times when we're thinking about variables or letters, we're thinking about an imaginary number, and it's really difficult to kind of grasp. So making yourself to be like in this case where they didn't necessarily assign a number to it, but they still made a visual, and that seems to be very beneficial. And now that we can see that this diagram up here, the picture it with the lines, really shows 7h and 5h, but we don't see this 2h squared. And the reason why we don't is because when we turn and we start thinking about exponents and things like that, we really start thinking about area and volume and things like that. So h squared is really going to be the area of a square that has a side length of h. And in the case, we can see right here h squared of our square with h, and to find the area we do length times width, which is how we get h times h, which can simplify to h squared. But when we have 2 of those, we don't just have h squared, we have 2h squared. And that shows the first box of h times h, and then a second box that also has h times h. So we can see h squared 2 times. And then looking down at the model it, they kind of take it a little bit further into the math tiles. And again, we have no idea what the value of h is. So in this case, we just see this is 5h. There's 1, 2, 3, 4, 5 tiles here. Over here, we see 7 tiles. We have no idea what the h stands for, but hey, there are 7 of them. And over here in the middle with our blue boxes, we can see the 2h squares that they talk about in that first expression. So as we are doing the connect it problems on page number 116, you really need to be looking back at your picture it and model it that are on page 115. And I know that you're going to have to kind of turn your page back and forth, but it's extremely important to make sure you're going back and forth. So it says, look at the picture it. If you combine the line that is 5h units long and the rectangle that is 2h squared units in area, do you get a figure that looks like the line that is 7h units long? So right now we're simply looking at, does it even look right? Because remember, we're trying to figure out if 5h plus 2h squared is equal or the same as 7h. So they're saying, if we took this rectangle that we know is 2h squared long, and we put it right next to this 5h, just like they would add them together in our first expression, would that even look remotely like the length that is 7h? So we're going to do that. I'm going to take, this is the rectangle that is 2h squared, and I'm going to add it, just like it tells me to, into my expression, to my 5h. So when I'm looking over here, I see 5h plus 2h squared. And if I put that rectangle right next to my line, and the question on number 19 asked me, do they look like they're the same length? The first one looks like it's significantly longer. So I'm going to go ahead and say that it does not look like it's 7/8 units long. It looks larger than that. And then looking at the model it, if you put the tiles representing the 7H together with the tiles representing the 2H squared, do you get the same set of tiles that represent 7H? So let's go back to 115. And basically what they're saying is, when I look at these as a whole, so if I were to take my shapes and I were to look at 5H plus 2H squared as a whole, does the model of 5H plus 2H squared look the same as the model of 7H? Do these two, does the one in the box look the same as the one out of the box? No, it doesn't. It says Richard says that 5H and 2H squared are like terms because they both have the variable h. Is Richard correct? Richard is not correct. Richard's very, very wrong. Because in order for terms, Richard is incorrect. In order for terms to be like, so in order for them to be like terms, the variable factors have to be the exact same. So in this case, the h, so the h in 5h, the h in 5h is just h. But the h, reminder, I can't write squared, so I have to draw it with a little caret to the 2. That right there shows you h squared. But the h squared, the h is in the h squared, the h is raised to the second power. So that number, if it doesn't have a number, that means it's basically being raised to the power of 1. And if you have multiple terms that are just h's, then you can combine them. What they're really trying to show you in number 21 is that you cannot at all combine terms that have different exponents. So in this case, I have h with no exponent, so in my mind I can think h to the first and h to the second. So when a variable is being raised to a power, that makes it a different term. So therefore, you cannot combine 5h and 2h squared because they're not like terms. And that's why when Richard said that and Richard showed that and we looked back at his work, we could very easily prove, hey, this is significantly longer. And in the model it, those two diagrams do not look the same. And the reason being is that they're not like terms. So for number 22, it says, is 5h plus 2h squared equals 7h a true statement? No, it's not. I mean, we kind of just disproved that, but we're actually, we're going to try to, so we proved that well, we haven't really proved it. We've shown that it's not equivalent by using our diagrams. But a lot of times when we're writing proofs, and as you guys get older, you will be writing a lot of proofs and stuff like that, you've got to use concrete examples to be able to prove yourself right or wrong. So in this case, it says substitute a value other than 0 or 1 for h and evaluate 5h plus 2h squared and 7h to support your answer. Okay, so I'm going to substitute in where h equals 2. And when I say h equals 2, that means that every single time I see an h, I'm going to substitute the number 2 in. So for the first expression, 5h plus 2h squared, I'm going to have 5 times 2 times 2, or I'm sorry, plus 2 times 2 squared. If I could find my caret, there we go. And if I were to find out the answer to this problem, the first step I have to take is inside my parentheses here. And I've got 2 squared, or 2 times 2, so I can rewrite this problem as 5 times 2 plus 2 times what 2 squared is, which is 4. And then from there, go on. 5 times 2 is 10. And 2 times 4 is 8. So now I've got 10 plus 8, and my final answer would be 18. And if I substitute in that 2 for h in my second expression, which was 7h, I get 7 times 2, because 2 is what h equals, and I just substituted that in for h. And my final answer for 7 times 2 is 14. Oops. So I can see that when I substituted the 2 in for both equations, I got 18 as one of my answers, and I got 14 as my other answer. And I can use this to support and prove that they are not equivalent. Number 23 says, apply the distributive property to write an expression that is equivalent to 5h plus 2h squared. Show your work. So this one's a little bit interesting. It's something that we worked on a lot last lesson, but in this case, we're going to be pulling out our common factor, and we're going to see something interesting. So when we're looking at 5h plus 2h squared, I can see that basically when we're writing this, 5h plus 2h, dang it, squared with my caret, this is showing me basically when I'm breaking this down, I see 5 times h plus 2 times, remember, h times h. Goodness gracious. And I can rewrite it that way because I know that h squared is actually h times h. And I know that when I have a number right next to a letter, I'm multiplying it. So I rewrote this as 5 times h plus 2 times h times h. And then from there, I'm going to pull out my common factor. And in my common factor in both of these cases is going to be h. So I'm going to pull that h out on the outside of my parentheses. And I know that if I needed to multiply h to get to 5h, I would have to multiply it times 5. And then in the same case here, when I broke it down to 5 times h, that really helps set us up for the distributive property. Because essentially when I break it down and I see a variable, I pulled that variable out. So when I pulled that variable out, I was left with just 5. So that's why I put that 5 there. Now I've got my addition sign. And I've got this 2 times h times h. And this one is interesting because I've got 2 variables here. So in this case, when I pulled out this h, the h to do the distributive property, I pulled out 1h. But if you notice, when I pulled out that h, I was still left with 2 times h. So when I'm writing this, I have to leave that because I only pulled out one of those h's. That other h was still left in that parenthesis. So when I try to pull this out for the distributive property, I'm left with h times the sum of 5 plus 2h. And to check myself really quick, all I have to do is redistribute that out. H times 5 is 5h. H times 2h. And in my head, I have to think, okay, well, I'm multiplying h times h. So I'm going to be left with 2h squared. So that right there, this distributive property checks out. And that is a great way to keep moving. So now we're going to go move on to our try it. Number 24. Are 3x plus 6 plus x and 2 times the sum of 2x plus 3 equivalent expressions? Use substitution to check your answer. So they're asking us, we have 3x plus 6 plus x, and then we also have this distributive property, 2 times 2x plus 3. We are going to substitute, that's what they're asking me to check whether these are equivalent or not. I'm going to substitute the easiest number that I know, and that number is 1. So when I substitute in 1 to 3x plus 6 plus x, I get 3 times 1 plus 6 plus 1. And now I'm going to go finish evaluating my expression or solving it using the order of operations. The first one, I'm thinking multiplication. 3 times 1 is 3, plus 6 plus 1. 3 plus 6 is 9 plus 1, and we get our final answer of 10. So now if I was going to check and see if these were equivalent, I must substitute the exact same number into the other expression. And if I get the same answer, that means that the two are equivalent. If I get a different answer, that means that they are not equivalent. So my second expression, 2 times 2x plus 3, I'm going to substitute my 1 in for my x. So I have 2 times 2 times 1 plus 3. And I'm going to start by doing 2 times 1 inside. I get 2 plus 3. I'll start with and then I'm moving on to my parentheses. 2 plus 3 is 5. And now I do my distribution. 2 times 5 is 10. So I can say that 3x plus 6 plus x and 2 times the sum of 2x plus 3 are equivalent. And so now moving on to number 25. Are 8 times the sum of w plus 6 and 5 plus 8w plus 1 equivalent expressions? Use substitution. So again, the easiest number to substitute in is 1 because it's the easiest thing to multiply. So let's substitute. We have 8 times w plus 6. So if we were to substitute that 1 in, we have 8 times 1 plus 6. First step in our order of operations is to get rid of the parentheses. 1 plus 6 is 7. So now we have 8 times 7, which is 56. So now if I look at my second expression, 5 plus 8w plus 1, and I were to substitute that 1, 8 plus 5 times 1 plus 1. And my first step in order of operations is that multiplication. So I get 5 plus 8 plus 1, and then 5 plus 8 is 13 plus 1. So we get a final answer of 14. So I can draw the conclusion that 8 times w plus 6 and 5 plus 8w plus 1 are not equivalent. Reminder that if the two answers, when you substitute the same number in for both expressions, if the answer is the same, then they are equivalent. If the answer is different, they are not equivalent. So again, these are going to be our guided practice of determining whether expressions are equivalent. Here is an awesome example to always return to if you need to. I'm going to do the next 3 problems up on the board. So let's dive into number 26. Simplify 6x cubed plus 6x squared plus 6x to get an equivalent expression. Label any properties or operations that you use. So when they're asking you to label the properties, that means are you using the distributive property are you using the cumulative property or are you using the associative property? And if you need a quick refresher, those are all on page 3 of your slides. So let's look at 6x cubed plus 6x squared plus 6x and come up with an equivalent expression. So when I can break down this, and I'm looking at these 3 terms and I'm trying to find of a common factor, they kind of made this one a little bit easy in that all the coefficients are the same and they are 6. So if I pulled that coefficient of 6 out and I got rid of that in all 3 of my terms, I could see that I could pull the 6 out and see x cubed plus x squared plus x. So now I've got 6 times x cubed plus x squared plus x. I can actually, so now that I've pulled out that coefficient and I'm looking at my distributive property here, I can actually determine that I can pull out another factor. There's another common factor between all 3 of these terms, and that is an x. So if I took one x out of each of these, and I pulled the x out and then I took away one x from each of these, my x squared would become just x, and my x cubed goes down to x squared. So now I can rewrite this as 6x times x squared plus x plus 1. And now I know you're thinking, but Miss Campbell, you pulled out the 6x. Why do I need to keep the 1 in there? And the reason being is that if you don't put the 1 in there when you go to distribute this, you will not get your final term of 6x if you don't include a 1 to multiply it by. So let's go back and distribute this and make sure that it makes sense. So if I were to multiply 6x times x squared, it would be 6 times x times x times x. So that becomes 6x cubed plus 6x squared plus 6x. So that looks to me like it will distribute right back out to our original problem. So we are going to add that into our answer key and move on to number 27. Number 27 says, Darla's living room is 12 feet long and 10 feet wide. Her dining room is also 10 feet wide. Write 2 equivalent expressions that each represent the combined area of the 2 rooms. So as you can see, they've already drawn you a nice diagram. And that is very helpful in making sure that, remember, I always like to combine the words with the diagram and then to the math, and it really kind of makes a trifecta in your brain, and it really kind of brings the subject matter home. So let's look at this beautifully drawn diagram that they have. We can see the living room, which is our first rectangle, and it's got dimensions of 10 by 12. And then it looks like the dining room is attached right next door, and it also has a width of 10, but we're unsure of the length of the dining room. Write 2 equivalent expressions that each represent the combined area of the 2 rooms. So the combined area is going to be area is length times width. And when I'm looking at this beautifully drawn diagram and I'm up here on my dry erase board, if I'm multiplying length times width, I can see my length is 10 and my width is going to be 12. My width is the 12 feet of the living room plus the width of the dining room, which I'm not sure of. It's an unknown number. That's why it has the x variable. But my length of both rooms are the same. So I can write this as 10 parenthesis 12 plus x. And the reason why I can write this is because if I were to find the area of just the living room, it would be 10 times 12. If I were to find the area of just the dining room, it would be 10 times x. And our common factor here is 10, so if we pulled that 10 out and got rid of that, we have 12 plus x. So that's our first equivalent expression. And then I want you to kind of think about this as, let's not combine them first. Let's figure out how much each is worth, and then we'll combine it. So we want to go back to thinking the living room is going to be, the living room on its own is length times width. And the living room has a length of 10 and a width of 12. And I want to think for the dining room the same exact thing. Length times width. My length is 10. My width is unknown, so it's an x. So I've got 10 times 12, which is my area of the first room, plus 10 plus x, which is my area of the second room. So if I take that and I kind of simplify that down, 10 times 12 is 120. So I know the area of my living room is 120. But because I have that x, I'm just going to rewrite it as 120 plus 10x. And that way we can plug in however that width is of the dining room. You can just plug that number in right there and you can determine the entire square footage of both rooms. So we came up with two equivalent expressions. We've got 10 parentheses 12 plus x, and we've also got 120 plus 10x. And for both of those equations, even though they look very different, if you plugged in x, you would get the exact same answer. And you can actually see the continuation of your first one. If you did the distributive property and you multiply that 10 times 12 and that 10 times x, and you get your second equivalent expression. So that works out very nicely. Looking at number 28, this is multiple choice. And it says, which expression is equivalent to 2 plus 3n plus 2 plus 9n? We've got A, which is 16n, B, which is 3n plus 8, C, which is 4 times the sum of 3n plus 1, and D, which is 4 times the sum of 3n plus 4. So it says combine. Remember, over here on the right in all of these, and throughout all of your lessons are these people, and those are your study buddies. They're very helpful. So let's look at this study buddy. It says combine like terms and apply properties of operations to simplify an expression. So when I'm looking at 2 plus 3n plus 2 plus 9n, and I'm trying to determine which of these are like expressions. So my biggest thing, and I learned this earlier in this lesson, when they said that I can't combine variables that are, squared or cubed, they all have to have the same amount of variable, or they have to have the same exponent. In this case, I'm looking at these two 2's, which have 0 variables on them. And I'm just going to quickly add 2 plus 2 together and get rid of that. So now I can go 4 plus 3n plus 9n. And remember, I am going to pull out my common factor here. No, I'm not. I'm going to combine those two. I got 3 plus 3n plus 9n. So when I just see that they're both n's and there's no 2's or 3's or exponents or anything, I'm just going to combine those two coefficients. So 3 plus 12, I got 4 plus 12n, right? So now I'm looking at these two terms. I have one term which is just a known number, and I've got another term which is a variable and an unknown number. And I'm trying to think, is there anything that I can pull out that both of them have in common? And I'm looking at my constant, which is 4, in the factors. Remember, so my factors for 4 are going to be 1 and 2 and 4. And then my factors for 12 are going to be 1, 2, 3, 4, 6, and 12. So my biggest common factor is going to be that 4. So I'm going to take that 4, I'm going to put on the outside of my parenthesis. And then I got to ask myself, well, what do I have to multiply the 4 by to get to 4? Well, got to multiply that 4 by 1. So 4 times 1. And then what do I have to multiply 4 by to get to 12n? So 4 times what gives me 12? So I know 4 times 3 gives me 12. But if I don't add my variable n into my parenthesis and I just left it as 3, I would do 4 times 1, which is 4, and then 4 times 3, which is 12, add them together, and then you get a final answer of 16, and you forget all about your variable. So when I pulled out that 4, I still have to think about that variable, and 4 times 3n is going to give me that 12n. So I can see that my correct answer, although mine has 1 plus 3n in my parentheses, remember, whenever we're doing addition and the commutative property tells me that it doesn't matter what order that they come in my parentheses. So my correct answer is C. And it says Anya chose D as the correct answer. How did she get that answer? So when she factored, it looks like she factored out her 4, just like we did. But when she factored out her 4, so when Anya she forgot to factor it out of the known number, which was 4. So when she forgot to do that, and if she were to go back and check her answer here, she would say, okay, I'm trying to get to, our original looked like this, but if you remember, we got to 4 plus 12n. She would do 4 times 3n, and she gets 12n, and that's perfect. And then her next step would be doing 4 times 4, which would give her 16. And that really shows us the incorrect answer. Because when she multiplied that 4 times 4, her constant was 16. And we know that we need to multiply, and our constant was 4. So we need to multiply 4 times 1. And that's why C was the correct answer. So I'm going to leave you with the independent practice. It's actually only 1 page today. You've got the 2 multiple choice questions and then the couple true or false. All I need you to do down here is move the smiley face onto true or false as you complete it. You can turn them into me on Google Classroom if you wanted to do them interactively online. You can also complete them handwritten in your remote learning book. Snap a picture of it and send it to me on my email. You can send it to me on Snapchat. But this right here, the independent work, is what I'm looking for. So I hope that our couple of lessons on expressions and equations are kind of bringing up some information that you remember getting when we were at Loris, and just that we're really kind of getting these foundational skills back under control. And there's a lot of foundational skills that are required throughout these lessons, these 6th grade lessons. So it's really important that not only are you doing these lessons, but you are working on memorizing your multiplication facts and things that are going to help you in the long run, going back and doing previous skills, adding and subtracting decimals, fractions, converting percentages. Understanding those foundational skills is really, really, really going to benefit you, not just in 7th grade, but for the rest of your math career. So this is a great time that you guys can, not only be learning new content, new 6th grade content, but also taking this time to really hone in on those foundational skills, which will make your math life significantly easier. On that note, I hope you all have an amazing rest of your week. I will be talking to you all on Friday. If you haven't done the Kahoot yet, make sure you get that completed. I just want to kind of check and see who our leaderboard is and how we're doing. So I hope you are understanding expressions and ratios, and have a great weekend.